My name is Jamaica Marshall, and I am a member of the CREST team. And some of you may know me as the coordinator for the Shadow the Scientist initiative. We're so very pleased to have you with us for this, our third session of Python and research tutorials for the year. Now, as a reminder, this tutorial is being recorded. The recording will be uploaded to the Shadow the Scientist YouTube channel later today, and I will be sure to send the link to all of you who have registered. Just a quick tip before we get started. If you haven't already installed Anaconda, please don't worry about installing it during the tutorial. We really want you to be able to be present and follow things as the notebooks are presented and to take notes. So because this will be recorded, you'll be able to go back through the recording after you install Anaconda and run all of the code. So please don't feel stressed if you haven't already downloaded and installed Anaconda. And thank you. I see everyone writing in the chat where they're from. So I'm here joining you today from the Big Island of Hawaii. And I'm very, very pleased to see such a wide variety of people. Okay. You will notice that you're not actually able to unmute yourself or turn on your video. And that's primarily because we really want to make sure that you can hear our mentors and that questions are able to be seen in the chat and in the Slack channel without having any disruptions. Now, as we get going, if for some reason the words on the screen are not large enough for you and you need us to zoom in, please put that in the chat. Let us know. If the volume it's too low, if we're talking and it's then the volume is too low, let us know. Drop a comment in the chat, please, because we really want you to be able to see everything and to hear us. Okay, so I am really loving all of the comments that we're getting in the chat where everyone's from. Okay, so before I introduce our mentors, there are just a few things I'd like to point out about the Python and research tutorials, because this is one of my favorite events to be engaged in throughout the year. Now, there are 5 features of the tutorial, and mainly, of course, we want you to have a good time learning how to code. And the PyaR tutorials, it's about coding in general, and this is what you'll be learning. Now, Python in particular is used extensively in a variety of fields, excuse me, including data science, data analysis, machine learning, data engineering, as well as web and software development. So Python is very flexible and adaptable no matter what area of STEM or STEAM you're going to be in. Now, the tutorials will be done using what are called Jupyter notebooks. Jupyter notebooks are fantastic because they are actually in a browser interface. You can not only see the Python code in your browser instead of having to use, a separate application, but it also allows you to see the results of your code after you run it. Another feature of the tutorials is that you'll be exposed to some interesting concepts. So specifically, you'll learn about the structure of a scientific journal article. Now, we'll be actually looking at an article from 2015. It's an astrophysics article, but journal articles in general tend to have a lot of similarities across various science disciplines. So you'll really get an understanding of those basic components. You'll also get to engage with some basic astrophysics concepts like stellar evolution. You'll learn about the Hertzsprung-Russell diagram and why it's such a useful tool for studying the various variety of stars. You'll learn about spectroscopy and the important role it plays in understanding stars and stellar evolution in general, Doppler shift, and you'll also learn about a few features of galaxies, like how their disks form and how they change over time through collisions and galaxy mergers. You'll also be engaging with some relevant mathematical and statistical concepts, things that you're probably already familiar with, like logarithms, standard deviations, which are used in a variety of fields, of course, outside of astronomy. Now, the main feature are our amazing mentors. I really want to highlight that. Not only have they agreed to share their time and expertise with us, but I want you to know that they are actively working in astronomy and astrophysics research. These are the amazing people who will be leading the various sections of the tutorials today. So you're not just getting some background on Python from people who are not actually engaged and using the kind of data that you'll be seeing in the notebooks, but they're actively working in this field. So please know that you have experts right here at your fingertips. Now, before I move on, I do want to make sure that I emphasize that there are two ways to engage with our mentors and with each other. First, you're already doing it, posting your questions and comments in the chat. So we welcome your comments and questions in the chat, especially your comments. Now, as far as questions, yes, you can put them in the chat, but we actually recommend that you use our Slack channel. So I'm going to put the link to our Slack channel here right now. This is the Slack general channel. And if you, now this was in the Zoom confirmation email, but if for some reason you haven't had a chance to join the Slack channel, go ahead and click on that link for me and jump in right now. You're going to meet two of our three mentors today who will be monitoring that Slack channel to answer your questions. Now, while you can post questions in the Zoom chat, as I said, there are several reasons why we actually prefer for you to put those questions in the Slack channel. The first is your questions will actually stay there. After you post any questions or comments in the Zoom chat, after the session's over, it disappears. It'll be in the transcripts, but that's a really challenging for our mentors to actually track and engage with. If you put your questions, if you post your questions in the Slack channel, they will stay there. So that not only allows the mentors to engage with you and answer your questions during and also after the tutorial ends, but it also allows for other participants who may have knowledge about the questions that you're posting. It allows them to also respond as well and for you to connect in a way that's really just not doable in the Zoom chat. So please, please do that. Now, you'll also notice that once we meet our mentors, there are three of them today, and there are quite a few of you. So because of that small number of mentors to wonderful participants, the Slack channel really helps because that way they can respond and engage with you and answer your questions and when they have the time and presence of mind to do so. So we appreciate you posting your questions there in the Slack channel. Again, any comments about audio or visual needs, please post those though in the Zoom chat. All right, without further ado, let's meet our mentors today. We'll start with Artem, then go to Geronimo and Apardito. Artem, welcome.
Hi everyone, thank you, Jamika, for the very warm introduction. This is so great. I'm very happy to be here and seeing all of you is so amazing. Um, So this is my first time at PyR, and I'm very grateful for the opportunity to be here with you. We have a wonderful team, and I'm so happy to be here. Yeah, so a little bit about myself. I'm a postdoctoral researcher, which means I graduated from my PhD. I study planets. I study their composition mostly, and I'm interested in a variety of processes around planetary formation, planetary evolution, planetary composition, and also a little bit about habitability. Um, and yeah, I do a lot of simulations, some of which do involve Python, some of them do not. But yes, I do use Python every day in my research because it's, like Jamika said, such a flexible, such a useful tool. And yeah, even though I only started to learn Python 1 year ago, so I started programming with a different language, and I switched to Python about a year ago. And I even had the opportunity to teach Python at university here in Santa Cruz as an instructor. So so I'm very excited to share my knowledge with all of you.
Fantastic, Artem. Thank you so much. Geronimo.
Hey everybody, my name is Jerónimo. I am currently a second year master's student. I am studying a master's in astrophysics, currently here in Nice in France. I've been connected a little bit with some of the activities by the Shadow the Scientist program for a while now, and I enjoy a lot like providing some time for it. I was able to participate in the previous PyR session. So this would be my second one, and I'm very excited to share a little bit, yeah, our experiences with the Python language and its applications into the astronomy and astrophysics fields. As Artem was mentioning, I also use Python fairly frequently nowadays. I learned it some years ago when I was using it for my undergrad a lot in different projects for different subjects. But nowadays I use it more than ever, I think, and it's a very useful tool that serves many purposes, and you will see how versatile it is, I hope. So yeah, welcome everybody.
Thank you, Geronimo. Wonderful. And Aparajito.
Hi everyone. I'm Apurajito. I'm from India. I'm in India right now. Uh, I graduated with a master's degree in physics, and I specialized in astroparticle physics here in India in St. Xavier's College, Kolkata. I have been working with Raja on a research project since 2021. Winter of 2021. And I taught myself Python back in like 2019 or so. I mostly use Python for my project almost exclusively. And I'll be leading one of the sessions. I have been a peer mentor in some capacity also since late 2021. I'll be leading one of the sessions today, and you will find me in the Slack channel and in the Zoom chat trying to answer your questions. As Jamika said, please put your questions in the Slack channel, in the Slack space. That helps us get to your questions so that they don't get lost in the Zoom chat, and so that they're preserved for people who might want to access the contents later. I only have to add to what Jamika said, that please be a little bit patient if we don't get to your questions in time. We are two people looking at the Slack channel, and there's a lot of you. So yeah, we might take some time to get to your question, but we will. And post your question publicly in the public channels. We encourage you to do that. And if you think you can answer each other's questions, if you have run into the same issue that someone else has, if you have solved the same issue, feel free to answer each other's questions. We encourage it. This is a collaborative program. Yeah, over to you, Jamika.
Fantastic. Thank you all so much for that introduction. And now I think we're ready to get started. So today we'll be looking at 3 different notebooks during the 3 hours that we'll be together. So first, we'll have Artem doing notebook 1, followed by Aparajito, who will talk about the structure of an astrophysics journal, as well as give some astrophysics background on the Andromeda Galaxy and the data set that's been used in the notebooks. Geronimo will present Jupyter Notebook 2 and provide a little bit more astrophysics background on stellar evolution, the color magnitude scale, that's the Hertzsprung-Russell diagram, as well as talk about the mass-luminosity relationship, which is really important. And Heather will close us out with Jupyter Notebook 3. All right, without further ado, let's go to Artem to get us started with Notebook 1.
All right. So thank you again, Jamika. I think that you should all be able to see my screen.
Yes.
Perfect. All right. So I will give you just a few, just a little moment so that you have time to open your Jupyter Notebook with Anaconda. So to do so, you'll have to launch Anaconda first, and then within Anaconda, you should find the app Jupyter Notebook. And then when you launch it, you will actually need to navigate to the folder where you downloaded all your notebooks. And then you can, and so you will have an interface like this. And so this is the Jupyter file browser. And then you will be able to open the notebook, and that will open this page. And so depending on your navigator and the version of Jupyter, the layout may be a little bit different, but you should be able to see the same content. So, all right. So let's start by talking a little bit about Python, what it is. And so Python is a programming language. And what is a general concept of a programming language is an app that takes instructions and performs certain operations. And so the purpose of this workshop is to learn how to use these instructions efficiently so they can answer your questions and so they can do the work for you. So you have some information here about Python, so feel free to read those in outside of this workshop. And so we are going to start programming now. So a quick word about Jupyter. So like Jamika said a moment ago, Jupyter is an interface to program with Python, which means that Python is a programming language, and Jupyter is an app that is designed to make it easy to program in Python and run different instructions. And so if you scroll down a little bit, here you will see the first instruction, the first piece of code that we are actually going to run. And so one of the most useful things to do in programming is to show something, is to ask the code to print something. And so this is achieved with this print function. And functions in Python, they take arguments, sometimes one, sometimes more, sometimes no arguments, but you always open the parentheses and you put the content of the function within the parentheses. And so what this line of code is going to do if I launch it is to print hello world. And so how do we do that? So you have to press inside of this cell. So this is called the coding cell. And then you go up and you press the play button. And when you do that, you see that here we have the number that moved up. That means that the cell was executed. It means that the instructions were run. And what is below the cell here, this is the result of the programming language, what Python did. And so all this line did is to print hello world. And this is sort of the first thing we do when we are programmers, is to try to show some message. And so below, for comparison, you have the amount of code that it takes to achieve the exact same result in Java. So this is a lot more convoluted. And so like it was said, Python is very flexible and very easy to use, and this is what we are interested in. All right, so scrolling a little bit below, so here you have some comments, and you will see this picture to show pitfalls. So I'm not going to comment on all of this, but feel free to read them. One thing I want to draw your attention to is how to make comments. So in these cells, you can execute code, but what is important is also to leave comments so that you know what each piece of code, what instruction are things doing. All right, so what's next? Are we only printing things? Well, not exactly. So that's just the beginning. And so one of the things we can do with Python is use the capabilities of your computer as a calculator. So allow me to, and so for example, you can do some additions. So here I am leaving a comment to say that everything to the right of this symbol is not going to be interpreted as code. And when I run this cell, so you have seen that the number has been incremented to 3 now. And what I am printing effectively is the result of the operation 2 plus 2. And so I can move forward and do other operation. And so again, I run the cell, and what I see is the result of 4 minus 2. I can do multiplications. And so, as expected, the result of 4 times 2 is 8. Divisions. Apologize, I have entered a dot, and here you will notice that the division of 4 by 2 is not an integer anymore. So before this cell, we had integer results, and now we have something after the decimal point. This will be commented a little bit later. And the last useful operation is perhaps the power operator. So when you raise a number to a specific power, and this is not the hat symbol that you would use on some calculator. In Python, if you want to use the power operator, you need to use the multiplication sign twice. So here we have 4 to the power of 2, and this will give indeed 16. So at this point, I also want to mention that in Python, spaces are not interpreted by the program. So make your code as well readable as possible, and feel free to add any spaces where you need. That is not going to change how the code behaves. You really can add as many spaces as you want everywhere to make your code nice and readable, and this will still, right, except for the leading spaces, of course, this will still work. And we'll see why leading spaces are important later. So far, we only done basic operations, but of course, the advantage of using something like Python is that we can compute some much more complicated results. So here I have the result of one big operation, and this is something that you could do on pen and paper, but of course, the advantage of Python is that this happens extremely fast. So this is why This is so useful in data analysis when you have a huge number of operations and very complicated operation that we want to run. And so right now, it may seem like the structure of a Jupyter notebook is fixed, but this is not true. You can add as many cells as you need, and you can achieve so by using the buttons on the right. So here you have buttons to move from one cell to another, and you can add cells above, cells below, and you can even delete cells. And so let's try, for example, to add a cell below. And so here I have a new cell to work in, and I can do some other operation like, I don't know, something like this, and I will divide that by 9 plus 5 to the power of 3. And so I just have to make sure that I am closing all the parentheses that I'm opening, and I can run this cell to print the result of this operation. And at some point, you will notice that there are a lot of shortcuts in Jupyter, and I will start using it. And as you can see, to run a cell in Jupyter, there is a shortcut. It's Shift-Enter. So you don't need to press the button at the top here. You can immediately press Shift-Enter, and you get the result. And again, like I was saying, the advantage of Python is that we can do operations that are as complicated as we want very fast, very efficiently. All right. So now let's talk about one very general concept to most programming languages. This concept is using variables to store some values. So think of variables as some objects that will contain some values. The way we assign a value to a variable is like this. So a equals 1. This is not a mathematical operator to say that a equals 1. In programming language, this means that we are taking the value of 1 and we are affecting it to the variable a. We're reading that from the right to the left. And then we're doing the same with the variable b. We are taking the number 2 and we are assigning it to the variable b. And so now, instead of handling different numbers like a and b, different numbers like 1 and 2, we can use variables to print their content. And so if I run this cell with either Shift-Enter or the Run button, what you will see is that we are first printing the value that is inside the variable a, and then the value inside the variable b. And so, of course, I can change the content of these variables, and if I run this, that still works. That updates the value of these variables. And again, if you have any questions, if anything is unclear, or if you, so feel free to leave messages on Slack. So moving on. So we just saw how to define variables, and like I just showed, you can actually reassign values for variable, and you don't necessarily need to have a whole number. You can actually put the result of an operation inside that variable. So in this cell, let me put these in comments for a second. And so on the first line, we are performing the operation 1 plus 2, which is equal to 3, of course, and we are storing this value in the variable a. And then we're printing the result in the variable a. So Shift-Enter. As expected, we see 3. Now, if I uncomment these 2 lines and I print what is inside up here, so a went from the value of 3 to the value of 27. And this is what we see when we print the variable a at two different places in the code. And so it's going to be very important to keep track of what is the value inside a variable when we're programming, because variables, like the name suggests, are going to change their value. And so a good mental exercise is to be able to keep track of what these values are. And just like with numbers, we can do operations with variable. This is something that you learn in math, and so this still works if we store some values in variables a and b, and then we do the operation a plus b. Then when we run this piece of code, then of course Python is going to print the result of 3, and I can change the values, and that is still going to work. So I can make it as complicated as I want, and that will still work out. All right, last but not least, one maybe useful feature of the print function is the fact that we can print more than one element. And more importantly, one thing to keep in mind about Jupyter notebooks in general is that variables are defined in the entire notebook at once. So what that means is that since the first time I have used the variable a in this cell, this is because this is the same notebook, this is the same variable a here, 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 and here. And so if I print the value of a here by running this cell, I will see that a is equal to 0.2 and that b is equal to 228. So keep in mind that everything you define in one specific cell is going to remain valid within your whole Jupyter notebook. This also means that you have to be careful about the order in which you execute your cells, because if you change the value of a variable, it is going to remember the last change you applied. So, and this is why this counter of cells is so important, because if this was executed as the 18th instruction and this as the 19th, then the value of a is going to be 0.2. But if I go back up and I execute this cell again, now I am overwriting the value of a to 27, the latest instruction. And so if I run the bottom cell again, then the result changes. So be extremely careful about the order in which we execute your cells. And for that, there is a very convenient button, which is this fast forward button, which actually forgets the value of each variable and reruns the notebook from the beginning. All right. And so, of course, there are many operations we can do on these variables. So one operation that is very common is to add a number to a variable. And because this is so common, there's actually a different syntax you can use, which is this one. So a plus equal 1, this is the same thing as writing a is equal to a plus 1. And similarly, if you want to multiply the variable by some number, then you use the multiplication equal sign. And this is the same as a is equal to a times 3. And so if a is 1 in the beginning, then we increment it by 1 and we get 2. And then if we multiply 2 by 3, we get 6. And so when I run the cell, of course, this is the result I get. And of course, feel free to change these values just to make sure that you understand what is going on. And so if I increment 1 by 50, I get 51, and 51 times 11, I will get 561. Right. All right. And so this is mostly it about the basic operations we can do for variables and numbers. And next on, we're going to see some different types of objects. Jamika, are we going to the end of this notebook in one session?
Yes, we are.
Okay. All right.
Thank you.
So, all right. So for now, we have seen how to operate with numbers and variables. And now let's see a different type of structure that Python can handle. Python can handle text. And in programming languages, text is referred to as strings. Strings of characters is what make text. So here we are seeing a structure that is similar to what we have seen before, but instead of appending a number to a variable, we're appending some text. By the way, let me comment that for a second. So if I append this text to the variable s and I run the cell, what I see is that I'm again printing some text. And what is very convenient with Python is that there are many built-in tools to manipulate those strings. So for example, if I take s and then I use what is called a method. So this is this is an interesting syntax, is that we're not using it as a function, we're using it as a method, which means we look at the variable s, and this point means we're accessing a property of that string. And the property we're trying to access is the lowercase version of that text. And so when we run this cell, what we see is that the uppercase letters H and W are now lowercase h and W, and the rest of the text is unchanged. And similarly, I can look at the method that accesses the uppercase version of the text. And so that, of course, gives me an uppercase version. And last but not least, when we have strings, we can use the method replace, which replaces specific chains of characters into something else. And so here I'm replacing world by zip. And so when I run that, I have this. Now, keep in mind that strings of characters are case sensitive. The reason for that is very simple, is because for a programming language, an uppercase letter is different from a lowercase letter. These are two different symbols. And so as such, it is case sensitive. So if I want to replace some characters, I need to make sure that I'm looking for the correct syntax. All right. So when we talk about operations on numbers, like 1 + 1, the result makes sense, it's 2. And some operations are also allowed to be performed on text. What does it mean to have some text plus some other text? Well, let's just try it out. So here I have a new string to which we append our previous string s with this text. And now you see the result on the first line is that the plus operator, it adds text together. And so similarly, we may wonder what happens if we do multiplication of a text by a number. And so as you may guess, this is kind of intuitive, right? Is if we multiply this string of characters by 2, then we get to time this text. And at this point, you may just be wondering how far we can go with that methodology. Can we divide text? Can we subtract text? Can we multiply strings by strings? And for that, I really suggest that you try for yourself, because programming is something that you learn by doing. And by trial and error, you learn the things that are possible and the things that are not. And so what I can try is, for example, to look at what happens if I multiply some text by itself, and I run the cell, and then I get an error. And this is perfectly fine. Making programming errors is part of the learning process, so don't be scared if you make any mistakes. The important part is that we learn something from that. And so here, what we learned is that in Python, multiplying a string by another string, this is a non-permitted operation. But what we can do is to add them together. We can add them, but not multiply. All right. And so this shows that we can manipulate strings of characters, which means we can create and manipulate text. Of course, we can do much, much more than just using lowercase, uppercase, and replacing. And sort of the operations that you will be interested in depends on the applications you want for it. All right, if there are no questions, we can move forward to another data structure. So we have seen numbers, we have seen variables. Now we just have some strings. And now let's move on to lists. What is a list? A list, like the name suggests, is a sequence of objects. It's a collection of objects that are indexed by some number. And lists are defined. So let's scroll to the next cell. In order to define lists, we define them with these brackets. So here, X is no longer a variable. It's no longer a number. It's no longer a string. It's a list that contains 4 elements, and each element is separated by a comma. So the first element is going to be 0, the second element is 1, the third is 2, and the fourth is the number 3. So let me comment the last 4 lines for the moment. So if I print the content of X, what I see is that it is a list. And now the way to access different elements of the list, we need to provide the index. And so, for example, if I want to access the first element of the list, what I need to write is X. I open the bracket and I put 0. The reason we put 0 is because in Python, numbering starts at 0. So the first element is the element number 0. And so if I run this cell, then the first element that I'm showing here is 0. Now, what I want to emphasize is that we just chose to have this list to be 0, 1, 2, 3, but I can absolutely change that to some different number. So just quickly generating something. And so now, if I run this, of course, I have changed the content of the list, and the first element here is 321. And so likewise, I can access every element of the list by providing the index. So which element I am trying to access, the first, second, third, fourth, and I get the corresponding element of the list. Now, if I try to go next, what happens if I go outside of the list? I get an error because there is no 5th element of the list. So this will not work out. So I'm going to comment that. And so in order to avoid such mistakes, there is a very useful function that is called len that provides the length of a list. And so in this print statement, I have some text that tells me just length of X. And then I am printing this value, which corresponds to the size of the list. And if I run this, then I get length of X is 4. And so if I change the length, so if I add some number, for example, 631, I run the cell because I want to update X. It is very important to run at each cell when you apply some change. And now when I rerun this, of course, the length has changed. Now we cannot access elements further than the length of the list, but one useful feature of Python is that we can access elements by looking from the last. So for example, if I print the -1 element, this actually represents the last element of the list. So think of it as counting backwards, right? The first element was the element with index 0. So if you access the element before 0, you're actually just going back from the last element. And so likewise, you can access the second to last, the third to last, and the fourth to last elements, and so on and so forth until you reach the first element again. All right, so this allows us to extract one element from a list, but what we can do is that we can extract entire arrays. We can take sublists from lists. And so the way to do that is to use this operator. So instead of asking for just one number, we're asking for a range. And here the range goes from 0 to 2. So that means element number 1, element number 2, and element number 3. And so, element number 1 and element number 2, because we exclude the last one. And so this is what I get from this list. And so, of course, the slices can be as big as we want. So instead of taking 2 numbers, we can take 3. Now, and so a couple of interesting features is that if we do not provide the starting point, or we do not provide the ending point, then the starting point is implicitly 0, and the last point is implicitly the end. So by default, if we don't provide anything, then it will start from the first element and end in the last element. And so as you can see, the syntax elements from 0 to 3 is entirely identical to take the elements from nothing to 3, because the 0 is implicit. And like before, this also works with negative indexes. So it may be interesting to think about what will happen if I run this last line. So we have nothing to -2. So the first number is 0 implicitly. So that's the first element. And then -2, this means the second to last. So which means that we're going to start from the first element, and we're going all the way up to the second to last. And so if I run this, this is exactly what I get. So as a reminder, let me actually add a line here where I print X so that we can keep track of all the elements in our list. And so this first line is our original array X, list X, and the last one is what we extract from it. All right, and so lists, just like variables, can be modified. So when we define a list, we can either modify lists as whole, or we can modify only single elements of that list. And the way it works is exactly like we were using variables. So we only need to find the element that we want to change and apply a new value to it. So for example, if I comment the last 2 lines here and I run the cell, so I erased my previous list and I replaced it by 1, 2, 3, 4. And if I only change the second element, then what I have is this new list with the new value for the element. And one of the most impressive things, in my opinion, about Python is that so far we have been using only numbers in this list. But in reality, Python can hold anything in a list. And when I say anything, I truly mean anything. It can hold a number, it can hold a string. An element of the list can even be a list itself, so we can have lists inside of lists. And these elements can be anything. They can be functions, they can be objects that you have defined yourself. This is something that will be covered in the future. But yes, lists can literally hold anything. And so here we have defined a list with a number, a string, and another list of numbers. And when we run this cell, what we see in the first, with the first print statement, this is the content of the list. And when we access the elements of the list one by one, then we are recovering from that list a number, a string, or a list. And so you may be wondering, with nested lists, with list inside list, how do we access individual elements of a nested list? Well, the syntax is as follows. You first access the outermost layer. So, and then you use the same syntax again to access the innermost layer. So think in terms of brackets, you're going from the outside to the inside. You work your way from the outside to the inside. All right, and so yes, I have run the cell. And so right now I just momentarily lost track of which cell was executed, and you see that having this counter is extremely helpful because it tells me what was the order of cells that I executed, and I know that I need to go below. All right. And so just like strings had these built-in tools to access lowercase, uppercase, or replacing some text, lists have also a set of tools, built-in tools, in order to manipulate this list. And so one of such useful built-in tools is the ability to create lists automatically. So and this is achieved with this function that is called range. What range is doing is that it takes 3 arguments. It takes a starting point, an end point, and a step. So we start at 1, and we go to 10 by steps of 2. And then we arrange the result of that in a list, and we store it in the variable x. And so when I run this cell, this is what I obtain, 1 through 9. So you will notice that with this function range, we only keep the numbers that are below 10. We're not going any step further. And the reason, and so you were wondering what is the purpose of such a list is, so of course, if you're manipulating very big sets of data, if you need many, very, very big lists to hold, for example, a list of people who are invited at an event, you may have arbitrarily long lists, which may be difficult to keep track of with pen and paper. But the advantage of Python is that it can handle huge lists without any problem, of course. And this can be arbitrarily large again. And so I said that this function takes 3 arguments, and actually a lot of these can be implicit. So if we do not state a starting point, then implicitly the starting point is 0. And if we don't specify a step, then the implicit step is 1. This is commented here. And this is what we see here, is that with only one number in the function range, we're generating numbers that start at 0 and go to 5, but again, excluding 5. And so this is what we get, something that goes from 0 to 4 by steps of 1. All right, so more operations on lists. So we saw that we can add numbers together, and that works with variables too. We saw that we can add text together, strings of characters. What happens when we add 2 lists together? Well, it just combines both lists. And so if I print the result of x plus y, what I see is the elements of x here from 1 to 9, and these are put in sequence with the elements of y, which are 0 to 4. And just like for strings, multiplying a list by an integer value, we are just repeating the list as many times as we need. And so in this case, I'm repeating the y list twice. And of course, feel free to change this. This is, in my opinion, one of the fun things about programming is that you can easily change what is inside of your code and rerun this. All right. So right now, when we look at this list, what we see is that the elements are not ordered. And just like for strings, there is a very useful method that can be applied to lists. And this method is called sort, which, as you may guess, sorts lists by increasing number. And so here I am I'm calling Z the list that is x plus y. And I'm just taking a look at Z first. And then when I am sorting the list, it actually replaces the list. And this is something quite important because it means that it does not just print the result of the sorting, it actually changes what your list is. So be careful when applying the sorting function because the elements get rearranged in the list. All right, and the last important thing with lists is that lists are dynamic, which means they can be changed both in content and size on the fly. And one very useful operation is to be able to add new elements to a list without having to declare the list again and again. And this can be done with the method that is called append. And so when you use append on a list, it will just add the element inside of this function. So if I start with a list that is 3, 2, and I append 1, then my new list is going to be 3, 2, 1. And if I append 0, then I get 3, 2, 1, 0. And of course, since lists can hold anything but text, any kind of object, we can also append some text. And so if I add these 2 lines, one that appends some text and one that prints the new content of X, then I have my new list. So it is perfectly possible to append different types of elements in the list. All right. Moving on to tuples. So these are dynamic objects that hold a combination of elements, and tuples are extremely similar. We define tuples with not square brackets, but with regular parentheses. And just like lists, it contains some elements that are separated by commas. And we can print lists and we can access their elements. The only difference between lists and tuples is that tuples cannot be changed. And so here, for example, if I try to change the first element from a lowercase a to an uppercase a, when I run the cell, I get an error. And the error is that tuples cannot have their elements changed. And so you may be wondering, why are tuples useful then? Well, tuples can be useful in a series of situations where you have some object that is not meant to be changed. And that can be, for example, I should have prepared that. It can be, I don't know, a list of people that are organizing an event and that are always present, and you don't want to mistakenly change the values in that list. And then instead of making a list, it may be useful to create a tuple so that to avoid changing its content by mistake. All right. So again, variables, strings, lists, tuples. In programming, in programming, there's one other very, very important type of data. These are called Booleans or conditional numbers. What are Booleans? These are variables that can only have two values, true or false. The reason why this is important in programming is because true or false usually represent the state of a circuit in binary. When we have 0 or 1, for a computer, this means true or false. And so these kind of type of variables are present everywhere in programming. And right now, let's see how they operate. So Booleans are a type of variable, so we can store them in a variable A and B. So let's have A that is true and B that is false. And so Booleans, unlike regular numbers, have their own operators. These operators are logical operators, and some examples of them are and, or, and not. So the logical operator, so some of you may have seen that in programming classes, but if you haven't, I'm going to quickly explain what this operation does. These different operators do. So the operator AND is taking two Booleans as input, and the output of that operator is going to be 1 only if both A and B are true. So if A is false or B is false or both are false, then the result is going to be false. And this is what we see here. Now, if I change B to true, then the result of true and true is going to be true. And if both are false, then it's still false. So for the operator OR, in order for this to be true, only one of them needs to be true at least. So if both of them are false, then I get false. But if one of them is true, or if both are true, then I get true. And in some places, we need to negate some logical operators, and this is achieved by using the function not A or not B. So here, if I say not true, then it's false, and for not false, then it's true. So right now, if this is something new, this may look a bit confusing, but it will make a lot of sense in practical applications that are just below and in the few examples at the end of this notebook. So when do we encounter these Booleans? We encounter them when we are making number comparisons. So for example, and so number comparison works in the following way. We have one number on the left, one number on the right, and some comparison operators. And for example, this first line, this is a double equal sign. It is what is doing, it is comparing is 1 equals to 2, and the answer, of course, is false. And if we ask, is 1 different from 2, this symbol is the not equal to operators, then of course we get true. And so this is where the Booleans come into play, because when we're doing numbers comparison, where the result we're getting is just, is it true what I said, is it true or is it false? And so some other operators are less than or less or equal than. We will use them in the situations where we need them. And of course, as usual, feel free to change the examples to see how that works. Now you see that 10 is not smaller or equal than 2. And likewise, you have the operators a greater and greater or equal to something. And so 10 is greater than 2, but 1 is not greater than or equal to 20. And so that is going to be extremely useful for making decisions in our code with if statements that we're going to see just below. Jamika, just a quick question. How are we doing on time? All right, I'll take it as everything is well. All right. So what are some of the applications? So like I was just saying, the reason we use Booleans is to orient the functioning of a program, which means that a program can change its path. It can change it can change how it operates depending on these conditions. So in this little piece of code, what we are looking at is a if-else structure. What are these if-else structures? The program is going to look at this first statement, which is a Boolean. It is going to be a true or false statement. And so if that statement is true, then we are going to execute the first line of code. If this is false, if this is not true, then we're going to execute the code that is below. And here, I would like to, and here the syntax of this structure is extremely important. So after the if instruction, we need to put a colon here, this symbol. And everything that is after the if should have an indentation. It doesn't matter how many spaces you add, but the general standard is to have 4 spaces. And so let's see what this code does. So we are affecting some value to the variable x, and we are checking if x is greater than 10 or not. If it's true, then we execute the first line, and if it's not, then we execute the second line. So here with x equals 5, this statement is going to be false, and so we're going to execute the second line. 5 is less than or equal to 10. Now, if I change the variable to 50, then the first statement becomes true, and we will execute the first line. 50 is greater than 10. And this is the basic block of workflow where we are changing the flow of the program depending on some condition. And so in the first example I just showed, there was just an if and else statement, but we can implement as many other statements as we want. So, and that is achieved with the elif function, that is short for else if. And so here I make a first comparison if x is greater than 10. And if that is true, then I will execute this line of code, and then the cell will be over. But if that is not true, the program will go down elif by elif to check the value of everything else. And so here I have a second statement to check if x is greater than 0. And so if I execute this code, and with x equals 10, so this is, so the first one is going to be false because we have a only greater symbol. but the second statement is going to be true because x is greater than 0. And now if I change x to a -10, then the first statement will be false, the second statement will be false as well, and then I will arrive to the third line. And naturally, if I use something that is bigger than 20, then the code will read this as true and execute only the first example. And of course, feel free to add as many elifs as you want. So we can add even something like this. And so you will notice that Jupyter understands when we put these columns that we're creating some if-else structure. And so when I skip the line, it automatically indents my line by the relevant amount of spaces. And I'm going to remove this. And so now I do -10 again, sorry, -5. Then I will end up in this intermediate line. All right. And so this is, and here we are learning some basic components of programming on how to make decisions based on some results. Another type of workflow structures are while loops. So while loops, as the name suggests, is going to repeat an action for as long as some condition is true. And it works very similarly as an if statement. We started with the while statement, then we provide some Boolean variable, which is a lot, and here it's a comparison of numbers. Then we tell the program to begin instructions, and everything that is below, that is indented, is going to be executed in the while loop. And for the moment, I'm going to, no, actually, I will keep this. And so what is happening here is that we have a countdown that starts at 3. And as long as the countdown is bigger than 0, we're going to print this value, and we're going to make this value smaller by 1. And so on the first execution, we will start with 3. Then from 3, we're going to 2, and then the loop repeats itself, and now it prints 2, then it's decreased to 1, and 1 is still greater than 0. So for 1, this is still going to work, but when the countdown reaches 0, this condition becomes false, and so we exit the while loop. And when we exit the while loop, everything that is not indented is where the loop ends. And so if I execute this code, this is what I get. 3, 2, 1, liftoff. All right. And so again, we started at countdown 3 and ended at 0, but I can, of course, start at some higher number, and this will still work. Now, I want to warn you about while loops. While loops can be slightly dangerous because it is sometimes possible to end up in an endless loop. So, for example, let me create a new cell, and if I do a loop like this, so 2 greater than 1. And I don't recommend running the cell. So in this loop, you will notice that this statement is always true. So the program will run this loop until something else breaks. So basically, this is an infinite loop, and this is something that we want to avoid. So be quite careful with while loops. They can be dangerous. And so I'm going to comment this to not run this by mistake. All right. So for now, we have seen loops and if statements on numbers. We can also make loops based on lists. And for that, we have this very useful structure called for. So the for structure is going to make a loop that iterates over elements of a list. So provided I have a list here, 0, 1, 2, 3, the syntax for something in my list, this means that I am creating a loop where this variable that I defined here is going to take the values of each element of the list. And so what this loop does, it simply shows the content of each element of the list. So if I run this, I just get here. And of course, like we said before, we can change these lists, make them arbitrarily bigger or smaller. We can have text or elements of lists inside of this. So let me define some list inside the list. And so if I run this loop, this is what I get. So because lists are ordered, they have an order from left to right, from 0 to the final element, then the iterator here, I, it doesn't have to be an integer. It will just be any element that is inside the list. And just like with the while function, everything that is indented is considered part of the program, part of the list. And as soon as we exit the indentation, we are not in the list anymore. So I can add as many instructions as I want. So I can print I can print I plus 1, I can print I squared. And as long as these lines contain an indentation, then we'll have something. Then this will be inside of the loop. And as soon as I don't have an indentation, this will be outside of the loop. And so if I run this, then this is what I get. So first I have 0, 0 plus 1, and 0 squared. Then I have 1, 1 plus 1, 1 squared. Then I have 2, 2 plus 1, 2 squared, and 3, 3 plus 1, 3 squared. I can even add an empty print statement if I want to make slightly easier to read. And so here I go, I have my 4 loops with the 4 elements. All right. And so just keep in mind that this indentation is important because this is what tells the code where the list begins and where the list ends. And so, of course, there is nothing that prohibits to have nested loops, which means to have loops inside of loops. So before running the cell, let me just show you real quick what is inside of range 2. So range is an object that can be interpreted as a list. And so here, this first list is going to have this iterator I that will take elements 0 and 2. Sorry, 0 and 1, because range doesn't go up to the last number. And for the second loop that is inside the first loop, we have the iterator j that is going from 0 to 2, 0, 1, 2. And at this point, it's important to keep proper track of the indentations, right? We have all of these 3 lines that are inside the first loop. And then we have this second loop with just this line inside the second loop. And so this is quite an interesting gymnastics that might be a little bit difficult to follow at first, but the more you practice programming, the more this kind of structure begins to make sense, and you will start to understand. It will be easier to follow what is being written in the code. And so this interior, this loop that is inside, it's producing these lines, these three lines, outer index, and actually there is a typo here I'm erasing. So the first word should be, sorry, this word should be inner index. So I is the loop that is outside, and J is the loop that is inside. So I is the outer index, and J is the inner index. And so what you see is that the inner index is the one that is being iterated first. And when we are done with this specific outer iteration, then we're repeating, but with a new outer index. So 3 additional loops. And so again, this may be a little bit confusing at first, but the more we use it, the more it makes sense. And it makes especially more sense when we're using it in real life problems where we are actually working toward a solution. All right. So we have seen how we use different workflows and how we define loops. And in scientific programming, one very useful structure to have is type of object to have is to define our own functions. And so functions, functions in Python are just like functions in the mathematical sense, where they take some input variables and they provide a result. So for example, when in math you have seen something like f of x, a function that performs some operation x, this is your own function that takes as the value the result of an operation. And so in Python, we can define our own functions, and the syntax is as follows. We use the short word def for definition. Then we have the name that we give to the function. This is something that we choose. Then we open the parentheses, and everything that is separated by commas are all the input variables. Then we finish the definition with a comma, and everything that is under an indentation is part of the function. All of these are operations that are going to be executed by the function every time we call it. And so the last thing is this return statement. This means what is the result that the function is actually giving as an output. And so in this example, for those of you who remember their vector analysis class, so x and y are some coordinates of a vector, and what this function does, it takes the square of x plus the square of y and applies the square root. This is the norm of the vector, the length of a vector. This is why we named our function norm and use n as the result. And so if my vector is for 3, by the Pythagoras theorem, you know that the length of that vector is going to be 5. And if you have a vector that goes that has +1 in the x coordinate and -1 in the y coordinates, you know that the result is going to be square root of 2. And of course, feel free to modify these numbers. And so naturally, it makes sense that the advantage of defining your own functions is when you have functions that you're using over and over and over and over again, and you don't want to type some instructions multiple times in your code. You just define a function and you use it. All right. So one important thing to keep in mind about functions is that everything that is every variable that appears inside of a function only exists in the scope of that function. What does that mean? This means that if here this variable dist is defined only inside of the function distance and not inside of the main code, this means that this variable is created when the function is run, and this variable is destroyed when the function is done. This quantity dist does not exist outside of the code. So here we have defined another function. This computes the distance between 2 points, the point of coordinates x1, y1, and the point of coordinate x2, y2. And so again, we can run this cell and we will get the distance, which is the result. Sorry, we will get the distance between these 2 points given these coordinates. And so, like I was saying, if I try to print this this value, this value dist, I will get an error because this is not defined. Because, like I was saying, dist is only created inside the function, and when the function is done, it does not exist anymore. All right. So we will comment that line and I will rerun my cell. All right, and so, yes, Jamika?
Thank you, Artem. I was just, I got a few questions that came to me, and they're kind of around the same thing, and it is the importance of having the knowledge of these foundational components. Like, the following notebooks 2 and 3, build on the having knowledge of these parts because you'll be using them. And the reason why I want to make sure that you get through this whole notebook is because the others you can go through and watch the recordings of them and run them yourself. But I definitely want to make sure that everyone understands these components. Could you briefly explain why it's important to at least be familiar with them before you actually try to use them?
Yes, of course. There are actually a few examples below of using all of these elements, all of these tools that we're learning about. So, for example, in the case of these functions, the purpose of defining some functions is that you define a sequence of instructions that you're using over and over and over. So, for example, if you have a code where you are computing distances between points again and again and again, what you want is to define a function that will do it for you so that you don't have to repeat some operation. And these functions, they can be as complicated as you want. So yeah, so this is just like some basic mathematical functions like sine or cosine that you want to be able to use in your code, right? And so here, the reason I define a function is because I want to be able to very quickly compute the distance between 2 points. And to do so, I just need to provide the coordinates of these points and I get the result. So instead of repeating all of these lines here, so the norm and this equation, I just provide the coordinates and I get the result immediately from there. So this is the purpose of a function, is to make your code more readable by avoiding the repetition of some equations. And so we will see further in some further example that as soon as we find a task that is being performed multiple times, we want to define functions to call instead of writing the code again and again and again. I hope that that emphasizes a little bit why we're doing this.
Yes, thank you so much.
All right. And again, feel free to ask questions in the chat if you, sorry, in the Slack, if you have any, and we'll answer them as soon as possible. All right. And so, again, and so not only, and so what I was saying before that is that these variables, they exist only inside the function and they don't exist outside, which also means that you shouldn't be afraid of overwriting them. So even if you use the variable called dist inside the function, this is not going to affect the result if you use the same variable name outside. In general, this is not necessarily the best way to program, but having one variable outside and the same variable inside the function is not a problem. And so when I run this function here, this will create one instance of dist inside, but it's not going to affect this string that is here. All right. And just a few more examples. Functions don't need to have an input. They can return the same element, for example. And so here I have when that happens, we still need the parentheses to because that is the syntax on how we define functions. But the operations inside are exactly the same, and we still return something. And so here, when I call this function that I have created, make a list, then y becomes the result of this function. So what is whatever is inside of the function. And so if I change the content of the function here to 35, of course, this changes how my function is defined. And function, so functions in the mathematical sense, they take some input and give some output. In Python, functions don't necessarily need to have an output. They can immediately work on whatever variable or object is being the input. And so, for example, imagine in some context, I need to double the size of a list. Double each element of the list. I can achieve it with the following function. So this function takes as argument the list that we want to work with. And then we create a loop. And notice that the loop is indented because the loop is inside the function. And then what the loop does is that it will go through all the elements in the list X, and it will reaffect, it will reappend 2 times the value of that element. So once again, this list takes X as an input, and then for each element in the list, for each index, sorry, it will take that element and put 2 times the result in the list. And notice that here I have no return statement because what effectively gets changed is the list X that we provided itself. And so if I start with a list that is 1, 2, what this function will do is that it will double the value of each element. And I can make my list a little bit bigger. And again, spaces are not interpreted, and then I get the double. And notice that I can call this function multiple times, double a list x and print x here. And so every time I call this function, I am overwriting the content of the list x. So I don't have a return statement anymore. I am directly manipulating the input of my function. So these are the two type of functions, the way we can program our functions. All right. So now, one thing that is important to keep in mind is that code is read much more often than it is written. All of these very small pieces of code, you notice that they are very short. They are very simple elemental blocks of programming, but they have a meaning, and we spend a lot of time reading them and using them rather than just coding them. So it is important to leave as many comments as possible and define what functions are made for, so that it is always clear to us why this function exists and what it does. And more importantly, what are the inputs and what are the expected outputs of that function. So below is one example of the function. So it's defined with this name, corners of rectangle, and it takes these.
Hey, sorry, Artem, can I jump in for a second? So I think we can skip this section because this part is pretty much completed in the notebook. And I think the learners can just go over this on their own. The import is something that we can explain in the second notebook. Since we're short of time, if you want, we can skip over this section. And we can take some questions and clear up what you've covered so far, because like Jamika said, this is the most important book, and let's make sure everybody has caught up to what we have covered so far.
Yes, absolutely. If there are any questions, I'm more than happy to answer them and go over some elements again, if something is not clear. How should we proceed for that? Should I check the slide?
Yeah. In the meantime, Jamika, if you want to say anything, I can switch to my screen. I can switch to the paper. We could set up for the next segment. And in the meantime, Artem can take some questions.
Yeah, that's perfect. Thank you, Artem. Thank you, Aparajito. And yes, I just put a question in the Slack channel. I got a couple of questions on some browser issues while downloading Anaconda. And so I put those in the Slack one, so for people to answer whenever we get a chance. Thank you, Artem, for going through this so thoroughly, because it is very important to make sure that we have a good handle on all of these various components that we'll need to use in the following notebooks. And you can find Artem in the Slack channel for a little bit. Excellent. Okay, so Aparajito is going to now take us through the structure of an astrophysics journal. And then while that's happening, Artem and Geronimo are still in the general Slack channel for any additional questions that you have. Aparajito, welcome and thank you.
Yeah, let me switch to my Chrome window. Okay. Yeah. Everybody can see my Chrome window now, right? Great.
Yes.
Yeah. So we just discussed the basics of Python, everything the very basic building blocks of the programming language. We will build on this with the subsequent notebooks. We will explore importing modules, importing functions from different modules. We'll see the power of NumPy, and we will work with some data that our research group, the research group that we're all connected with in some way or another, Raja's research group, Raja being the person who brought us together in this program. That group has collected a lot of data and will be working with some of that. This is, of course, meant to be a program that focuses on scientific research applications of Python. That's the lens that we're, approaching Python through. But you can use the skills somewhere else. These skills are transferable. And since we have spent the past section of the program covering the programming part of it, I'm going to now switch over and give you some background on the astrophysics part of it. And eventually we'll be able to combine these two and see how that goes. This entire tutorial, this entire PyaR program is based on one research paper by one of Raja's former PhD students, Claire Dorman. All right, and you can see that paper here. Let me zoom in a little bit. So this is the paper. It's called A Clear Age Velocity Dispersion Correlation in Andromeda's Stellar Disk. Now, that's quite a mouthful, right? And to be clear, you don't need to understand every single tiny detail about this paper. We will make sure that you understand the relevant parts of it. So you can see that Claire here is the lead author, and this name here is Raja. Puragragoha Thakurta is his proper name, but he goes by Raja. Before we get into the paper, let's see where the data comes from, all right? And it comes from this thing right here called the Andromeda Galaxy. Some of you might have heard of it. It's the nearest major galaxy to the Milky Way. The Milky Way being our own galaxy, that's where we live, in the universe. And the Andromeda Galaxy is the nearest major proper galaxy to our own. So Andromeda Galaxy is one of the most well-studied galaxies because, well, one, it's nearby, and two, it's in some ways very, very similar to our own. It's a spiral galaxy, which means it has a very similar structure to our own galaxy, to our Milky Way. And understanding Andromeda better helps us understand our own past, our own galaxy better. So it's nearby, it's very easy to study, and it's very similar to the Milky Way in some key aspects. And there are a number of ways to study it. Specifically, the one we are going to explore in this tutorial is through studying the Andromeda Galaxy spectrum, okay? This paper right here by Claire Dorman is the foundation of this entire tutorial. So we'll explore what this paper looks like. We'll explore what a scientific paper in general looks like, a peer-reviewed scientific paper. And we'll see which parts of it we're going to recreate. Okay, so what is a research paper? A research paper is literally just a presentation, an organized, compilation of the work that you have done, collected, and described in detail. So in a way that the entire world can understand if they speak this technical language. And, a scientific paper is supposed to be a way to communicate with the entire scientific community. So I can write a paper from India and somebody from the US can read it, and an academic from the US can read it and completely understand it, right? And if they want, they can check whether or not my data, my analysis, everything is correct. First of all, we have on the very first page a title of the paper that gives you, in one line, what the paper is about, followed by the authors of the paper. The very first author here is usually the lead author. They are usually the person who are writing the paper, and followed by everybody else who has worked on the project, everybody else who has contributed to the project in some capacity. And you can see that the paper will also always list the affiliations of everybody involved, of each of the authors. And right after describing the authors, right after listing the authors, we jump straight into something called abstract. So the abstract is a one-paragraph summary of the paper, right? It tells you exactly what is contained in the paper and very briefly what kind of results we have presented. An abstract is the entire paper compressed into one paragraph. And it's supposed to help you judge whether or not a paper is something that you want to read for your work, if it's relevant to your work, if it's relevant to your research. You're supposed to read the abstract, and that should give you enough information. That should give you enough of a clue on whether or not you want to read the paper in more detail. Also, there are certain aspects like the date, when it was published and where it was published. You can usually find it throughout the paper, in the headers. Abstract is a summary, and it gives you the context and the main points, like I said, along with the very brief indication on what the results and conclusions are. Followed by the abstract is a structure that is the introduction. Let me move the bar right here. Okay. Followed by the abstract is the introduction, and then we describe the actual work by describing the data, how it was observed. We analyze the data, we draw conclusions. There are figures here, and you can see that it's a very long paper, and we end it with the conclusions of the paper, and finally the citations. So let's go over each of the key sections here in a little bit more detail. So we started with the introduction always. As the name suggests, it gives you the introduction to the project, What is it about? What is the paper about? Why we're doing the work that we're doing? What prompted us to do the work? In this case, we are also going to give a brief introduction, to the background of this research, what came before this research from our own group and from other groups, followed by data acquisition and reduction. This is like a feature of an observing astronomy paper. If it's some other kind of experimental, science paper, it will have a slightly different heading here. Maybe you'll call it data and methodology or something like that. You can have two different sections, one for the data and another for the methodology. But for observational astronomy, it is data acquisition and reduction or something similar. So here we tell we tell the reader about our survey that the data comes from, which is the SPLASH survey. And it stands for the Spectroscopic and Photometric Landscape of Andromeda's Stellar Halo. That's a lot of words to say that we point a telescope at the Andromeda, we take the light and we split up that light to make a rainbow out of it, okay? Those rainbows are called spectra. And when you do that for a lot of stars, thousands and thousands of stars, that's basically a survey. Whenever you take data from thousands of different objects or hundreds of different objects in astronomy, that's basically called a survey. And in our case, it's a spectroscopic survey, which means we're working with these basically rainbows, right, of starlight. Now, the key thing here about the data section, about the data or the methodology section, is that it should have enough details for anybody else in your field to be able to recreate the study, okay? That is the very foundation of modern science, of peer-reviewed publications. It should be something that can be recreated. Otherwise, it's just, like an opinion. It has to be provable. There has to be an evidence, and that evidence has to be verifiable. And you need to describe exactly how to find that evidence, right? And that's what you're going to do here in this section. So it's a very detailed section. And then we go into, you can see that there are subheaders here in that section and others. Let's see. You can see that there's a method section right after the data section here. Like I said, there are two sections. It is separated into two. You can see that the method section gives you the entire workflow of how we arrived at the results. And finally, we get into section 4, which is the results. And like the method tells us what we did, and it tells the world what we did in a way that they can recreate it if they wanted. The results section tells the world what we found after we went through that process, right? After we conducted that experiment or did that observation. And the results, you can see that there's a lot of plots here, which means we're presenting a lot of the data here. There's in a lot of the results here, the data from the results, not the raw data. And finally, there's a section on discussion, where we actually discuss what the findings mean. So far, we have only stated what the findings are, now we need to interpret those findings and explain exactly what the significance is, why they matter, why anybody should care about them, and how, how it's relevant to the field, how it's extending the knowledge of the field. And finally, there's a section called conclusions right here. Where's it? Here. Yeah, that's discussion and this conclusion. Yeah. Wait, is there a conclusion section? Sorry, it's taking me so long to find it. Okay. So there is not a separate conclusion section in this paper, but you can have a separate conclusion section from the discussion. But here it's rolled into one. Instead, we have a summary, which you can have also besides the conclusion and besides the discussion and conclusion. And summary is basically usually a step-by-step or like a bulleted list of the main highlights of your paper. So it's kind of like the key findings in a little bit of detail, but not too much. A little bit more detail than in the abstract, but not as much detail as the previous sections. And finally, there could be a section on acknowledgements. And then we end the paper with references, right? So the references are basically previous work. It is previous work in your field that you use as supporting evidence for your work. And you don't have to cite every single claim you make to some previous work, but some absolutely need to be cited. Here's a little example of what should or should not be cited. For example, do you think the statement, the sun is about, the temperature of the sun is about, say 5,700 Kelvin, right? The surface temperature of the sun is about 5,700 Kelvin. Let's say I make that statement somewhere in my paper. Do you think it is something that I need to cite? Please put it in the chat. Do your guesses in the chat? Just a yes or no.
There was a question about the summary.
Sorry?
There was...
Oh, this is a question about the summary. Is that summary at the end? Yeah, it is the summary at the end. Yeah, like I said, so the summary is basically like a highlights reel of the key findings of the paper. And you can see we discussed the velocity dispersion, which is the main subject of the paper for the RGB, HGB, and the MS stars. It's usually a bulleted list. But you can just roll it into a few paragraphs. Right, so somebody said no in the chat, a direct message to me. And that is the correct guess. You don't have to cite that statement in your paper because it is a well-known statement. The second statement, let's say, I say the temperature of the young sun was insufficient for liquid water to be present on early Earth, despite evidence that liquid water was present. That's quite a more detailed statement, right? And that's a claim. So do you think I need to give a citation for this claim if I make it in my paper? Once again, put your guesses in the chat. I think somebody just said yes. Yeah, that is correct. That is something that we have to cite. So well-known statements, things that are well-known facts that everybody in the field already knows. We don't have to cite those. But if it's a little bit more niche, if it's something that needs some backing, that is not, a widely accepted statement, you will have to cite that. And this is a complete list of citations here in the references section, all right? And finally, at the end is something called an appendix, which is literally just extra stuff. It's the stuff that's not directly relevant to the paper, to explaining the paper. But it is additional information that anybody who is looking to recreate the results might be interested in. Now, I skipped one of the pages here that I want to go back before I end this section. Right. So what we'll be doing, okay, just a quick recap. A paper basically starts with an introduction. Then we go into data and methodology, which could be one section, or in this case, it's separated into two. And then you present the results, which is basically what you found. Data and methodology being what data you used and how you collected that data. Results being what you found, and then discussion and conclusions, which could be rolled into one section, could be two different sections, could be two separate sections, which basically analyzes those results, tells the audience why exactly the results matter. And finally, we ended with a summary, which is like a highlights reel of the paper. And then the final section of the paper is a list of references, okay, of previous peer-reviewed work, peer-reviewed or not peer-reviewed. Anyway, so I want to come back to one of the key features of this paper, and you'll see that there's a lot of figures in this paper, right? A lot of plots. We were going to recreate some of these plots throughout our tutorial. That's going to be basically the whole goal of this tutorial, to recreate the plots in this paper, some of the plots in this paper. And you can see that the figures are very, very, very important to a scientific paper like this. It gives you the results at a glance. Instead of throwing a table of numbers at you, I am presenting it in a visual way that's easier for people to understand. And it could be maps like this. It could be, scatter plots, graphs like this. Plots come in a lot of different shapes and sizes. 1D, 2D, a lot of different plots. They should be clear. They should be properly labeled. Each axis should be properly labeled along with units and a scale. And every figure in a scientific paper comes with a caption that tells you what the figure is about, what it's showing, and a figure number that can be referenced somewhere in the body of the text. All right. So, yeah. Yeah, that's it. That's it for this section. Please tell me if you have any questions. You can put it in the Slack, you can put it in the Zoom chat.
Pardito, one question I got
Yes.
to me was on the process for writing a scientific paper, like what is used to write it. And I shared that I had used LaTeX before. Maybe you could speak about that really quickly before we go to the next one, and maybe if you've used a different software program, you could talk about that.
Yes.
Sorry.
So,
To add to that question,
yes.
on top of that, what Jamika just ask you, is it possible if you could also share this commented version, the link maybe to that one, because someone was asking if they could have access to this one because it's very useful to have all the comments.
I can share it.
Jamika could arrange that. Yes, thank you.
Thank you.
So, like Jamika said, she used LaTeX to write her papers. And that's exactly what we use in astronomy too. You can see that the font here is something that's really, really clear. It's easy on the eyes. And there's a lot of scientific notations and equations in the paper. So we use a programming language called LaTeX. That's LaTeX, and it's not pronounced latex. It's pronounced LaTeX. There are many different programs that use the LaTeX language. I use something called Overleaf. It's a website where you can just use the LaTeX online to create documents. It could be a paper. I use it for reports, for my CV, a lot of different stuff. So yeah, and LaTeX has really cool features that make writing scientific notations very, very easy. It makes adding references, linking to things very easy. Adding hyperlinks from one section of the paper to another, adding hyperlinks to figures, to tables, and you can include figures and tables in very visually pleasing and very legible way. LaTeX is an extremely powerful tool that's purpose-built for writing scientific documents. Yeah, that's the answer to your question, Jamika. Any other questions? Let's see. Chat. Overleaf is an online version. MNRAS stuff could be looked at too. Yes, MNRAS is basically a visual style. It's not really a software, as far as I know. This is not a scientific research paper be available to us. Yes, Jamika will make that available sometime in the near future.
Yes, I just
Till
put it
then,
in the Slack channel, but I'll post it
great.
here in the Zoom chat too. Thank you.
Perfect. Please check out the Slack channel. It should be present there. Avi asks, how are these papers published? Good question. So this is a peer-reviewed paper, right? Which means it goes through a peer review process. What is a peer review process? Well, you know how when you post something on the internet, and sometimes people are annoying to you, and they try to come up to you and then say, actually, this is not how things work. It's this other way, actually. So scientists do that professionally, but we do it in a very organized and civilized way. We write a paper and we send it out to a publisher. The publisher then sends it out to our peers, so other scientists, other academics, not just science, this goes for all academia. So astronomers will get the papers, astronomers will be peer-reviewed by other astronomers, historians will be peer-reviewed by other historians, specifically in their niche fields. And basically, when you get a paper to review, you try to find flaws in the paper, and you give feedback on the paper. Explain its shortcomings, explain where it could be better, and make sure that it is sound. The arguments that they're making are sound. The methodology is sound. The conclusions are sound, and there's no plagiarism, or there's no plagiarism is something that basically usually the editor looks out for, but you try to make sure that there's no data manipulation, that everything is kosher, right? And once you have debated it professionally, once you have been annoying to each other professionally, you can be sure that the paper will stand the test of time, hopefully, until somebody comes along with something that's even more well tested and improves on your work. So that's the peer review process. And once it goes through the peer review process, the publisher publishes it. Who the publishers are and how they make money off of the papers, while the scientists don't make any, that's a whole different subject. Academic publishing is very, very exploitative, but that's a whole other topic. Yeah, that's how peer-reviewed papers are published. There are other kinds of publications that are not peer-reviewed. Conference proceedings, conference presentations, oral presentations or posters, stuff like that. That's not usually peer-reviewed. Yeah, that's your answer. Also, quick note, Jupyter linked an archive link. That's something called a preprint. So that's something that where we publish a paper that's currently in review, right? That we're going to send out for peer review. It's basically putting a paper out in the world to kind of call dibs on it, right? Before it's peer reviewed, because peer review can take a long time, and you don't want somebody else to, snatch your work and publish it for their own or something similar. So you do something called a preprint for free. It's not behind a paywall, but once the paper is peer reviewed, along with additional data, it is put behind a paywall, usually with the journal, unless it's open source, open access. Yeah. So you can just go to archive.org to usually access the preprints. Most scientific publications, especially in astronomy, have a preprint these days. Yeah. I'm going to stop sharing my screen, and I'm going to keep answering questions in the Slack. Yeah. Over to you, Jamika.
Thank you, Aparajito, and thank you for the questions and comments. So if you weren't able to open that first link to the annotated paper, you should be able to open the second one. I see several people say that, yeah, they haven't. Excellent. Thank you so much. All right. So we've had Aparajito, we've had Artem, and now we're ready for Geronimo. Geronimo is going to, I guess we'll probably just have time to really hit the basics of Notebook 2, and we typically end up kind of needing to go over, but we'll look at that next time. So we'll just take this next 48 minutes for Notebook 2. In the meantime, Artem and Aparajito are in the Slack.
Yeah, I also think, I mean, Notebook 2 is not very lengthy. It doesn't have
Yeah,
to take that long, and it's actually easy to summarize it because we're gonna go
excellent.
over some things that Artem already explained pretty good and completing some stuff on extra functions we'll use. And then if you want, we could also give, like if we have time, I guess we can give a little bit of the astrophysical context and prepare ourselves for starting to check out Notebook 3. I think we have time for that, but we will be able to finish at 9. I mean, I'm saying my local time
That
at
sounds perfect.
noon. Is it noon in Western, right? So in Pacific,
Yes,
in Pacific time is noon. Okay,
That's
perfect.
right.
Let's do it.
That sounds great. Thank you.
So, okay, so hello again to everybody. I hope you've been enjoying the session so far. Let's have this second notebook that hopefully will complete some things that Artem was mentioning, some useful stuff as Parajito was also telling us. A lot of these tools will help us um, get to the end goal of kind of replicating some of these results, which when you're when you're starting to get close to the process of publishing, like making and publishing scientific results, it's a bit tricky to understand. It feels like magic when someone presents to you a beautiful plot, a beautiful graph of different, like displaying information, transforming astronomical images that we get from telescopes into data that involves a lot of brains put together to conclude stuff from what we observe in the skies. So I hope this will keep adding up to making that a bit less mysterious. So in this notebook, let's start to see how we can display information and how we can handle big amounts of information, because with Artem we were seeing that you can have like these lists of numbers that now we're gonna use as arrays. Like it's a very useful data structure that we will be using more. It's not the same exactly as the lists or the tuples that Artem was mentioning, but they're even more powerful. So we're going to start working a lot with them. And to work with them, we use this library called NumPy. And here, this is the standard way that we were seeing before of telling our Python environment, our Python code, that we're going to call some functions that are not native to Python all the time, but they're saved in some different library. In this case, the library or the packages that we're importing is called NumPy, and we can give it a nickname. So in this case, it's going to be anything that has np dot something is going to involve a function that is not native to Python in general or to the Python standard library, is going to be in this NumPy library. And same happens with this matplotlib.pyplot library. This is going to be the one that we use most of the time to display information visually, like to do a graph, to plot things, and we usually use the nickname PLT. When you have this, when you're importing libraries, you can use any nickname that you want, but this is the standard. Like most people will call NumPy NP and matplotlib.pyplot PLT. And this one is just a little comment, like a little, it's called like a magic command that we can use within the Jupyter application to make it close with this screen, so it doesn't pop out any other windows to show any of the plots we're gonna do. So okay, here we can start exploring again the thing with arrays. So as we saw earlier with Artem, there was like a range function, just range without the A here, which is native to Python. We didn't need to import anything else to create a range, like a list of numbers that had a start and end point and then a step, but it had to be an integer step in that case, if I'm correct. In this case, we can change that and have a bit more flexibility in the arrays that we can construct with the help of NumPy, who's going to create an array of numbers that start at 0 and at 100, non-inclusive. So it's not going to involve the number 100, but it's going to stop right before 100. and it's going to take a 0.5 value step. So it starts with 0, and then it adds 0.5, and it creates the next number, and it keeps adding 0.5 and saving those numbers in our array, which in this case we are assigning to the variable x. So x is going to be an array. So we can start by printing that. So we can just execute this. Oh wait, very important. We need to first import all libraries. I didn't do that before. And now we print our array. So first line we're doing after creating the array is just printing it. So it shows us that we have these 200 elements that go from 0 to 99.5, because that is the last element right before 100. And each of them is separated by 0.5. So this is a very useful function that we will be using a lot to generate sequences of numbers. You're gonna find that a lot, that it's necessary for you to generate a sequence of numbers, because sometimes you need to do things with those numbers. Like, for example, if we want to plot a function, which is what we want to do in this case, we would like to start plotting functions and seeing them. So you need like a field of numbers that you're going to input to the function, and then it's going to do something with them. So you can get your images or your y values for these x values that you're generating. We can use a bunch of the functions that Artem was mentioning, like the length function, this len, len, of an array. It will tell you how many elements the array will have. So in this case, this array is one-dimensional. It has just a list of numbers, and it has 200 of them. So it says the length of x is 200. A couple of very useful functions is also the mean function. So we can calculate the average value of the normal average value of the total amount of elements that our array has. And then two very useful ones are the min and the max of our array. In this case, we generate the array is ordered, like we know very well how it's distributed. So we know like the first element is 0, the last element is something almost 100. So in this case, 99.5. So we know that the minimum is the first element, the maximum is the last element, but this is not going to be the case for many arrays that we will be working with, because sometimes you have a list. For example, if you collect like a survey from people and you have 200 people and each person gives you their age, for example, you don't know exactly where, what is the maximum. If I just give you a table of 200 numbers, it's useful that NumPy just tells you that. You don't have to go through the whole table and find which one is the max or which one is the minimum. So you can do it just with these functions. So that's very useful. As always, you can play around and change this, the way you build the X array, the way you involve the other functions that we can use to get more information about the array we're working with. So okay, now we can use that array to see or to visualize two functions. The NumPy is very, very useful and it's very smart. So I can use that X array that we just generated as the argument of a function. That is very interesting, because what it's going to do is it's going to calculate the value of that function with each value of each element that the array has. So it's going to create a new array, or in this case, two new arrays, y1 and y2, which are going to be arrays of the values that correspond to the function evaluated in each position of the previous X array. So in this case, it takes the X element number 1, the first element, it divides it by 10, and then it calculates the sine function of that, and it saves it in the Y1 array. Similarly for the cosine. So it does two of them. So I'll have two new arrays that have the same length as the previous array we were working with. But it's going to have, instead of the numbers from 0 to 100, it's going to have the values of the numbers to 0 to 100 divided by 10, and then calculating sine or cosine. And you can do this with whichever operation you would like to do it with. So let's do it. In this case, we don't get any output because we're simply evaluating that and saving it into a variable. So now my notebook knows that, okay, there's two new variables. There are these two new arrays that are called y1 and y2. So now we can use this matplotlib library that we were talking about, that is very, very useful for making figures, for making plots. And this is very, very cool. So first, it's very, very simple. If you just want to make a plot, it's enough to just run this command. I'm going to add an extra cell just to visualize that right here. If you simply write plt.plot and you give it two arrays that have the same size, if the two arrays are equal in length, Matplotlib is going to read that and understand that you want to plot on the x value. So the first array that you're giving it takes as the x values, and it corresponds each of those x values with the y values that you're giving it at the second position of the function. If we simply run this, it will give us this very nice sine function. So it looks cool. But here we want to do something more sophisticated. So to the plt.plot function, the plot function that we want to work with, we can add labels. So we can call our this, if we're going to plot different curves, for example, we want to add like a little legend on the side that tells us what corresponds to what. Like we don't just want to show a bunch of curves and then no one knows what corresponds to what. So that is very useful. So we can call each, for example, this one will have the label sine and this other one will have the label cosine. So then when we display it, we will know which is which. And also we can differentiate them by giving them different colors. So you can add the variable or like the parameter color, and you can simply between quotes write the name of a color, and most of the normal colors Matplotlib will understand and will try to assign that color to the curve that you're drawing. You can also personalize how thick the line should be, because yeah, sometimes you might need something that when you print it or when you show it in a presentation, you want it to be very visible, so you need a thick line, or if it's too thick, you can just make it thinner. So you can play around with these values if you want to see how it impacts. And then also we can change the line style to make the label show. So we need this to be visible. We add this little empty function legend. If you just leave it like that, it will show whatever labels it has. And then it has some more specific parameters. If you need something very specific, you can Google a little bit and check the documentation. We can also restrict the amount on the y axis. In this case, you can also work with x lim or y lim to specify how zoomed in each axis you wanna be, right? So this is also done automatically, but also you can set it manually with a range between. So you want here the y values to go from -2 to 2. So you run this, and let's run it. Here you can see that we have on the y-axis from -2 to 2 as we specified. We have two curves that are differentiated by color, but also by the style of the line. And it also gives us the little legend right here that makes it clear like which curve is which. And that's very useful. And that makes a very, very powerful tool to display data. So I really like it. Here we chose the dashed style of line, but you can also, for example, if we put here a colon, it's gonna do it dotted. Or there's many different ones. For example, I think if you write dot dash, it should do a dot dash line. Or yeah, if I get an error, I can also read that it says, it probably says that this one that I wrote is not a valid value for the line style. So LS is line style. Support values are this one. So I wrote it backwards. It's not dot dash, it's dash dot, I guess. But yeah, but if you make a mistake in that one, it will usually tell you what alternatives you could use so you can correct it. And when you run it, it works. So that's very useful. Here, there's a couple more lines that are also useful. When you display data, it's very important because you are the one plotting. You're running your code, you're plotting something, you know what you're plotting. But when you show the plot to someone else, they don't know what you were plotting originally unless you write something on the axis. So we can create X labels and Y labels that tells us, okay, this is going to be the X quantity in the X label and the Y quantity on the Y label. And on this these two names that you assign, you can write whatever you want. X label like hero, right, like this. And you see it shows whatever you write on it, and it has an attribute that is the font size. You can also make it larger or smaller as you like. So that's also very useful. So yeah, so now we can try a new one. Let me run this so we can talk on top of having the plot visible. So yeah, we can play around. if we try to define some new functions on top of this X array. So remember that the X array was an array from 0 to 100, if I'm not wrong. Yeah, from 0 to 100. But if we override that, if we run again X equals something else, then Python knows that we're reassigning it to something new. It changes whatever we called it before, and now it's going to be this new array that is it's going to be between 0 to 1, and it's going to take steps of 0.01. Okay, so it's going to start at 0, add 0.01, and then save that new value, add 0.01, add that other value, and all the way until it reaches 1, and it will stop before having to write 1 in the array. So we can define these 3 functions. One is going to be, let's take, not even functions, these are just operations we're running on the X array. So the first one is going to be, let's create the Y2 array from cubing, like taking the cube of the X array. Then we can do another one, Y3, just by taking the square root. If you, this might be a weird way to write it, but if you see this is X, the X array, elevated. Remember that 2 asterisks is the power function. So it's the power operation. So it's X to the power of 1/2, 1/2, and that is mathematically the same as taking the square root. So this will be the square root of the X array. And then we can do something a bit more complicated, like, okay, let's do twice X and then subtract the square from that and see what happens. So we can define as many arrays from doing operations on an original array as we want. And then we can plot all of them one on top of the next one. If you want to plot several things, you just write the plot command as many times as you want with the different operations or the new arrays that you're including. As always, the important thing is, in this case, by construction, we built the Y2 array from running operations on the X array. So they have the same size, you know, each element of the X array had an operation done in itself, and then it was saved as an element of the Y2 array. So it's going to be fine. But sometimes if you want to mix arrays that come from different functions or come from different data sources, you want to make sure that the two of them, if you want to plot one against the other, the two of them have the same size or the same lengths. So yeah, here we can run the same, and similarly, here we're doing some, not just the empty legend, we have a specific location that we want to define. So if we write 0, it takes that as the top left corner. So it's going to put our legend, this little square, on the top left. If we wanted to have a specific font size, then we can change this number and it will just do it as you ask it to do. But if I erase this little line here, it's also going to work because it's just going to choose those values automatically. It chooses like the best possible spot, which in this case, it chooses the same corner, but look that it makes it a little bit smaller. So that's also interesting. And when again, we can define the X and the Y label here. And it's also with the specific font size that we choose. So this is a way to build plots in Matplotlib that is very, very compact and useful. Notice that in this case, in contrast with the previous one, we didn't use the color. We didn't define like a specific color for each of the plots that we ran. If you notice on the previous cell that we did for the sine and cosine example, we explicitly wrote color equals magenta, color equals blue, and then it gave us those colors. If you don't do that, there is like a specific order that Matplotlib chooses colors and decides to display them, and it does it automatically. If you don't specify it, it still works. It will just assign them automatically, and it will not ask you about it. So yeah, most of the time, if you don't have a preference for the colors of your plots, you can let Matplotlib just do its thing, and it will work. Also here, important to note, we are using this label. Remember that we had the label in the previous one. We wrote label. We just wrote in quotes, double quotes. For example, y equals sine x, and we did it with normal text. There's something very, very nice, very nifty that if you remember, we were talking about LaTeX earlier. LaTeX has a specific way of writing that makes things look fancier, makes things look good. For example, I'm gonna do something here. I'm gonna write it just like we did for the previous example, which I think would be useful, which is if I use double quotes here, and I simply write y equals, and then I'm gonna use, write it like, oh wait, x to the cube, something like this, x cubed. And I write it like that. See that this one is like normal text, like if you would display it, I don't know, from your normal keyboard in normal text editor, it will look like this. But if you write an R before the quotes, and then you use the dollar signs to write your mathematical expression, you can use LaTeX notation or like this more fancy, I don't know the exact name of it, but yeah, in some sources I've seen it like it's like MathJax or like this visualized like math notation, which is way nicer. So instead of having to see it like X with the explicit power symbol to the 3, you can simply write it in a more compact way and it looks much better. So that works by adding this R, which means like raw input, I think it's something like that, like a raw, raw text source. And then after that, it will understand that if you put some things between the dollar signs, it will understand that it's going to be in the LaTeX style text. And then it even works like some things that are going to be within the dollar signs are going to be on that style. But even if you add something after that that is going to be normal text, I will write just text. It will work. It will just simply use the fancy math notation for the things within the dollar signs, and then we'll use normal text for the rest. So that was the last comment on that. I think you can explore that a little bit more, try to display different functions and see if you can make your plots fancier. That's always very fun. So yeah, I don't know if anyone has any questions on this bit, or if we can use this last 15 minutes to explore the astrophysical background a little bit. Let me know.
Harold, I think it should quickly highlight the differences between a Python list and a NumPy array, because they are going to be using NumPy arrays throughout the tutorial. They just learned about lists, so why NumPy arrays are more powerful and how they differ.
Yes, okay. So let me see. I think I have the previous, the intro one right here. And there was a section on lists also, so I can have both right here. Yeah. So see how lists are this little lists of numbers that we define in this way. I think we were seeing how, for example, if you run an operation on a list, like taking the double of a list, let's copy this. For example, if I copy it right here, so we can display it here. So if I call this list, and then I create an array, which I can use the np.array function. So this tells Python, okay, this thing that I'm gonna put in between this function array, I want it to behave like a very specific object, and it's different from a list. So let's do the same. So we have these two objects that to us, let me display it with print command list, and then so apparently to our untrained human eyes, these two things might look like the same, and we would say, okay, these two things are the same. But remember how, for example, if I try to calculate the double of a list, what it does is that it concatenates. This is a very specific operation. It concatenates the list twice with itself. So it takes, this is going to give the same result, I think, if we just write my list plus list. Yes. So it just concatenates, it puts two lists together as if they're, doesn't matter if they're different things, it will just put them together. Arrays are more powerful because usually we don't want to do things like that. Sometimes we want, it might be useful for data handling, you know, maybe you have different tables and you want to put them together. But most of the times you want to take like a ton of data, like a bunch of data elements, and you want to do the same operation to all of them like we were doing earlier. So instead of that, let's go back to the ×2 so we can like that. Instead, if we do that on the array, look that what we get is that each element of the array got multiplied by 2. So 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4, and so on. So it's way more powerful in most cases because what we want to do sometimes, for example, we're going to do it for the activity of notebook 3. We would like to, for example, make a whole array of values from the FAT dataset, for example, or the splash dataset, and you have like measurements of how bright stars are in one color and in another different color, and it's very important for astronomers to subtract those two quantities. So you want to take two arrays and subtract them, and you don't want to like just put one on top of the other like when we do that with lists. No, we want to do that same operation with two different arrays and get a new different array that has the same size and keeps some of those same properties. You also want to run sometimes, I don't know, if you have an array of temperature values and you need that temperature to translate into something else. You have a mathematical relationship that from temperature give you, I don't know, brightness, stuff like that. You can do it through having an array of all those values and doing operations in the array and getting a new array. Not the way that the list handles it. I don't know if that covers maybe what you had in mind also, Aparajito. Maybe if you want to add something.
Yeah. I think you covered it in detail. Arrays are very efficient and they are faster. So, if you want to do a mathematical operation on every single element of a collection of numbers, so if you're doing that to a list, you will have to run a loop and go over every single element individually. But if you want to work with, but if you're working with arrays like Hero showed you, you can just put it in a NumPy function and it will spit out another array that has operated on every single element, and it's much faster. It's much more versatile. It is exactly the kind of stuff that you need for handling a lot of numbers, for handling big data.
Yeah, I was just thinking about that earlier, that Artem was explaining the loops. Like I think more like after I started using Python a lot and mainly using NumPy arrays and like array-based arithmetics, it's very rare that you have to use again loops.
It's very rare.
I really don't use loops that often. It's more normal that I just do operations on arrays and it's very fast. It's very effective.
Yeah.
So yeah, I don't know if there's any other question, any other topic we want to dive a little bit into, or we can talk a little bit in the next 10 minutes about stars. What do you think? Yeah, I think this one is not super long, I think.
I agree.
Okay, so let's have a quick talk about stars. Hopefully, right?
Yes, we can see it now.
Okay. I'll go back to this last bit where I was in, so you can see the whole presentation. I mean, I just went through mentioning this list of different characteristics or features we can measure from stars. So it was just this list. So at least I hadn't shown any important plots or anything so far. So yeah, as I said, we measure temperature, distance, radius, mass, magnitude. The magnitude is kind of tricky. Also, it's a tricky concept sometimes because it's kind of weird to give a number to how bright a little dot looks in the sky. So it could be a little bit abstract, but it's also very useful because we somehow will need to quantify that. And that brightness will be connected to something very important, which is the luminosity, is how much energy it's actually emitting. And that is very, very relevant because we want to know exactly how much, truly, because when you see a star in the sky, you're not really sure if it's very bright because it's very close to us, or if it's very bright because it's, even if it's far, it's still huge and it emits a bunch of energy into space. So it really, really is luminous. So it's important to measure the actual luminosity or the power that the star is shining with. So for that, it's very common to use solar luminosities, comparing it with our sun, or the power unit watts, which if you look closely to some devices in your home, you will see that it's a normal measure of power. So if you look like a light bulb or like any electron drives, it will usually tell you how much watts it like consumes or emits. And the color, for which we use the very original quantity we call color, but it's not exactly just green or blue or red, right? It's something that we assign a number to through measuring the stars in different bands. So show you that briefly. So first, the magnitude scale. It's kind of weird, but you can get used to it. I would encourage you to try to go get a catalog or like a little sky map, or in Wikipedia also, if you Google some star names, you will see that it will have a magnitude value assigned to it. And the tricky thing is that negative numbers are brighter. So the more to the left on this number line it is, the brighter it is. So for example, to put it into perspective, the sun is something that can have an apparent magnitude of around -27. The full moon can have something, I mean, or the moon in general, depending on the phase, can have something on between -10 up to -18, or around those values, depending on the exact phase. So it is if it's very negative, you already know that it's very bright. And then you have the normal stars we see in the night sky are usually between -1 and 6. And then beyond 6 is usually seen as the limit that our eyes, like our bare naked eyes, are capable of noticing in the night sky. So if something is fainter, so like it has a magnitude value higher than 6, then it's harder to see by our eyes. Then we will need something that can collect a bit more light for longer or on a bigger area. And that would be a telescope camera that can hold for like some exposure time, and that is very, very useful. So then we have something called apparent magnitude, or you have also absolute magnitude, which is like apparent magnitude is what I'm saying. If you look in the sky and you see how bright something is from Earth, so you're here just chilling in your backyard, looking at the night sky, and you see different brightnesses. You don't know exactly if it's because one of the stars is very close to you, even if it's small, it looks bright, or if it's very far away, but it's super bright, right? So that value we give to how it looks just without knowing distance, it's apparent magnitude, because that's how it appears. And then we define absolute magnitude, which is how bright it actually is, by imagining we can see the stars all in line at the same distance from us, which is distance defined as 10 parsecs. So if you put any star at 10 parsecs, like you imagine you can move it and see it from 10 parsecs away, then you have like a fair comparison to see which one is actually brighter, which one is actually more luminous. And this is very important, and it's very tough to measure, because you need to know the distance to the star to be able to measure that in a more accurate way. So yeah, I have a couple more slides on this. Do you want me to close it up and maybe continue tomorrow, or we
Yes.
can take like 5 minutes for me to finish this? Let me know.
I think we can take the next 5 minutes for you to finish that. Thank you, Geronimo. And I did just drop the
Perfect. Yeah, no.
presentation and the slides in the chat. So anyone who can't access it, just send me a quick comment directly. Thank you.
Perfect. Okay. So I mentioned something about measuring color. The thing is, we cannot know exactly how much how bright a star actually is in all the light spectrum. I don't know if you've seen that there is like a whole rainbow of colors that our eyes can see, but then there's more beyond that. You know, the radio waves that our cell phones or our I don't know, a radio equipment can catch and interact with. But also you have the microwaves we can use to heat our food with. You can also have the X-rays, the infrared waves. You have the ultraviolet that is very important to take care from the sun's ultraviolet range. So there's a lot of ranges of light that we don't see with our eyes. And even the one we see, the range we see with our eyes is not, we don't see it fully or the same because each of our eyes will be slightly different. So similarly, it happens with the cameras we use to take the pictures and measure the magnitudes of the stars with. They can only see very well a specific color, like a specific range of wavelengths. Like we can characterize color, the color of light with a number, which is the wavelength. How long or short are the waves of light that travel from the source to us? So a specific color will be connected to a range of wavelengths, and with that we can define for sensors for the sensors that cameras use to capture light. We can define a system of specific windows that we know exactly how wide they are and how efficient they are in capturing the signal in that bandwidth, right, in this window of wavelengths that we're looking at. So if we standardize that and we tell all the astronomers in the world, use these specific windows to measure your stars, then we can all know exactly how bright stars, how bright are the stars that we're measuring, right? Because we're using the same scale. If each astronomer used a different scale, it would be madness. This was the case some centuries ago, and then a guy named Pogson noticed this and said, like, no, we need a more refined way to measure magnitude. And then after that, the photometric systems, which is something like this, UBVRI is a photometric system, made life much easier and much useful for astronomers all over the world. So there's a very important thing, and is that if you observe a specific star, it will not shine as bright in one of these windows as in another. So if in V or I, it will look a bit different because some stars will really be more red or more blue when you look at them. If you go to your backyard and look at the night sky, you'll probably see that there's some stars, if it's a clear night, some stars are going to be more like bluish, some of them are going to be more orangey, more red. So that means that they emit more in one of these bands than in the other. So a useful metric we can have to describe color is the difference between two of these filters, and we can define like that the color. So if you define it with like a more short wavelength, so like bluer color, so here we have, for example, V is somehow more to the left than I, so it's like a bluer filter. If you subtract the two of them, so you subtract the V minus the I magnitudes, you define a color or a color index that if it's small value, it means that it's a bluer object. If it's a larger value, it's a redder object. And that's a way to quantify the color of an astronomical source. And that is a very useful thing. So I think if you want, we can continue this on the next session, so I don't take too much time from tonight's. But it's, yeah, I think it's a good point to stop before introducing the color magnitude diagram, which is what will be dealt with in notebook 3.
Perfect way to wrap us up, Geronimo. Thank you so much for leading us through both of these sections, notebook 2, and I'm really getting us started with some of this, important foundational information about magnitudes and color, just the astrophysics background. So in the Slack channel, there's a link to that annotated paper that Aparajito was presenting on, as well as a link to the slides that Geronimo was just using and talking to us about. Please drop a message in the Slack channel if you aren't able to access it for some reason, and I can work on that. In the meantime, please remember that your Slack, anything that you post in Slack will remain there. And so once you are able to access the recording, which I will have up in the next few hours, once you look through it and run the code yourself, any questions that you have, please just drop those in the Slack channel and they will be addressed by Artem, Parajito, and Geronimo. In the meantime, I'd like to thank you all for joining us, and especially our mentors for sharing their time and expertise with us, Artem, Parajito, Geronimo. Thank you so very much.